So, hi everyone, welcome, have a good afternoon. Welcome to this session on create your own serverless PKI with .NET and Azure Key Vault. Quite a bombastic name, but we'll get into it. But before we dive in, I'd like to start off with a little story. Now, our story begins at one of my customers, who was not a software company. It was a hardware manufacturing company. This company was making devices which were supposed to operate in manufacturing lines in factories worldwide. And they did have some developers, but these developers were tasked with writing the software to run the hardware. And they released a new hardware once every couple of months, every year, and that was the release cycle. Until one day, they wanted to connect these devices to the cloud. They want to take data from the devices, send it up to the cloud, analyze it, and then visualize it so that both themselves and their customers will be able to see and have insights into what is happening with their devices, effectively turning it into an IoT system. And that's where I came in. So I came in, we started analyzing what do they have, what do we need to do, what are the requirements, what are the constraints. And one of the biggest challenges that we immediately saw that we're going to have is security. How do we ensure that the devices are actually who they are? How do we authenticate them? How do we authorize them? Meaning that how do we know that a device is allowed to send a certain piece of telemetry? How do we send this data confidently so that we know that no one else can see this data because this is very sensitive information for the customers? Now, these problems have many solutions out there. We didn't need to invent the wheel. Every system out there has these problems. But since this wasn't a software company, it was a hardware company, we wanted to keep the solution very simple. We didn't want to have it hard to maintain. Our solution in the first place was supposed to be a serverless solution running on Azure. We wanted it to be serverless, so it would be relatively easy to maintain, no infrastructure. It was really quite a simple solution. And all the developers were .NET developers, so we wanted the solution to be in .NET. Now, it turns out you can't solve this problem with .NET and serverless, although you probably won't be surprised that the documentation on these issues is not so good. Okay, it's very hard to find the documentation. It's very hard to find samples for these things. And we did a lot of work in figuring out how to do it properly, so that's why I decided to create this session to share my knowledge. So today, we're going to start off with talking about an overview of what is an IoT system, an IoT data ingestion. We'll talk about it in a minute or two, no more. Then we're going to give a quick overview of what's a public key infrastructure, or PKI, what are certificate authorities, and what are certificates. And for the majority of the session, we'll talk about how do we build a serverless certificate authority using .NET, how do we issue certificates from the certificate authority, and eventually, how do we use these generated certificates in order to confidently and securely send data from the devices to the cloud, and I'll show you the sample working end-to-end. Now, I'll show you a lot of code during this session, and you'll see me using Visual Studio. All the code is open source on GitHub. You'll have the link to the repository at the end. It's built with branches, so you can follow along each step of the demo. And so you'll have the code later on. No need to take pictures of it or something like that. My name is Eran. I'm a CTO of a software services company from Israel. We're called Code Value. I'm a software architect, software consultant. I've been dealing for the recent years, I've been dealing a lot with cloud-based systems, both AWS and Azure. And as a result, I'm also recognized by Microsoft as an Azure MVP and also a Microsoft Regional Director. So let's get to it. How does a typical IoT data ingestion pipeline look like? Well, first of all, obviously, we have our devices. We can have tens of devices, hundreds of devices, even millions of devices. In our use case, we expected to have something around several thousands of devices in the end. So it's not a big system, but it can scale up to millions if we want to. Then we need a way to securely send data from the devices to the cloud. We have pieces of telemetry, events that are happening in the real world, and we want to send them. Now, Azure provides a service which is called an IoT Hub, which allows us to ingest this data rather easily. It allows us to manage the devices. It allows us also to send messages to devices. I won't go in depth into IoT Hub. That's a topic for another session. Once we have the data in the cloud, we can send it later on, either save it in raw storage for later processing, or have some sort of stream analytics, or online alerts, or whatever it is we want to do. Again, I'll touch mostly on this part right here. How do we connect security to the cloud, and how do we manage it? Now, in a real scenario, you might have more than one pipeline, because, for example, you might have multiple customers in a multi-tenant system, and you want to isolate between them. Or in our case, we were geographically spread, where we had customers in the US, and customers in Europe, and customers in Australia. And mainly due to regulation issues and privacy issues and data sovereignty issues, we wanted the data to stay in the US, in Europe, in Australia, and so on. So we need to have multiple pipelines. But we also needed a way for the devices to know when they're booting up, who should they talk to? Which customers do they belong to? And for that, again, Azure provides a service which is called the Device Provisioning Service, which acts as sort of a router. We can register our devices. The device connects to the provisioning service when it boots up. The device provisioning service then has a set of rules, which I'll show you later on how to configure. It registers the device to the IoT Hub, returns the credentials, and then the device can directly communicate with the IoT Hub. Okay, so this is the scenario. I'll show you at the end. This is the scenario we're building. But we're not going to talk a lot about IoT. We're going to talk about security and .NET, the certificate authorities. Now, I said that the devices want to connect securely, and we have three things that we want to achieve. We want to achieve confidentiality, meaning that no one else will see the data we're transmitting because it's sensitive. We want to authenticate the devices, so if a certain device says it is a certain device, then we know who the device is. And to authorize them, see what they can do, or check that they are allowed to do something. Now, all of these typically rely on something that's called TLS, Transport Level Security. You might also know it as HTTPS or SSL for earlier versions. And most of the solutions rely on this protocol for securely transferring data from one side to the other. TLS, in turn, relies on certificates in order to create the secure channel, in order to create the trust between the different parties of the conversation. So basically, we need a way to issue certificates to devices as they leave the factory, and then be able to manage these certificates, renew them, revoke them as necessary, and so on. And again, we wanted to do it in a simple manner because it's a hardware company, it's a .NET company, and we wanted the security solution to align with the rest of the architecture, which was serverless on Azure. So that's what we want to build. So what is a public key infrastructure to begin with? A public key infrastructure is basically an umbrella term of stuff, okay? This is the best term to describe it, of stuff that we need in order to issue certificates. It can be to issue them, to send them to the destination, to the devices and install them, to store them on the device, to use them, to revoke them, to alert someone that the certificate is about to expire, to monitor it, and so on. So PKI is an umbrella term for everything that we need in order to handle the certificates. Now, typically, you don't want to build it from scratch, okay? It's a solved problem. Everybody's doing it. You don't need to create it by yourself. So there are multiple off-the-shelf solutions that you can use. They can be open source, they can be cloud-based, they can be hybrid, and so on. Or if you have your own unique scenario, like the one we felt we have, then you can take some parts off the shelf and write others and emphasize the things that are unique to you. You don't need to build everything by yourself. So that's a PKI. What is a certificate? A certificate is basically a computer's equivalent of a driver's license. It's a driver's license for computers and code. Much like each of you has their own driver's license, and the driver's license has your picture on it, and a name, and a way to check that the driver's license is authentic, that no one faked it. Okay? So when you want to identify yourself, you show your driver's license, and someone can see, okay, this is your picture, so that's you. It looks authentic, so the government gave it to you, so you trust the government. And I can see the picture, I can see that it's actually you. So I know when you have your name, you identified yourself to me. The same thing happens with computers or certificates. Basically, a certificate is a binding between a name, an identifier. It can be the device name. It can be the website domain name. It can be anything else that identifies whatever has the certificate. It's a binding between the identifier and the public key. Now, I'm not going to go deep into public keys and private keys and cryptography in this session, but I will tell you that that asymmetric key cryptography is the basis for all the encryption and digital signatures that we use today. And the public key is something that you can show to others that can let you prove that you are the owner of this certificate. And once you prove it, and I'll show it to you in a second, then the other side, the other device, the other service knows that you're actually who you claim you are. You are the identifier. And we'll get to that in a second. Now, I'm sure you also heard the name X509 certificates, X509 certificates. X509 is just the name of the binary encoding, the way we encode the certificate when we send it or we write it to a file. So a lot of times you'll see encode X509 certificates. Basically, that's the only standard used today. So it's roughly the same to call it a certificate or X509 certificate. The certificate authority is the entity which issues these certificates. So in the driver's license example, we have the government or the state verifying who you are, and they do it by various means. You have to go there, or you need to have some other ID, and they ask you questions, and somehow they know who you are, and they give you this driver's license, this certificate. Now, when you verify the certificate, you don't care how that entity verified who you are. I trust that they did the work. The same thing with certificates. We have various certificate authorities in the world, DigiCert, GoDaddy, and so on, who we trust. And once someone shows a certificate issued by them, then we know that we can trust that their identity was verified. So it works on trust. So just to show you how a certificate looks like, so I can open up my browser, go to, for example, let's say GitHub. And you know this lock icon which appears up here when you're working on a secure channel. I can click on it. You can see I have a certificate here. And I can see the information in the certificate. So I can see that this certificate, for example, was issued to GitHub. The certificate authority was DigiCert. And I can see more information. I have all kinds. These are called X509 extensions. All kinds of information on the certificate, the main one being the subject. Who is the owner of the certificate? And I can also see the public key itself. In this case, it's a public key. It's an RSA public key. And this is the length of the key. So this is what a certificate looks like. So how does it work? When we create a secure channel, how do we prove? How do we use the certificate to prove that we are who we say we are? So in our case, we have Alice and Bob. And Alice wants to open a channel to Bob. So she opens the channel, says, "Hi there, I'm Alice." To which Bob, the service, replies, "Hi Alice, I'm Bob." And then Alice wants to know, how do I know you're really Bob? How do I know you're really who you claim? How do I know you're GitHub? How do I know you're Google? And so on. At which point, Bob gives her the certificate, much like we saw GitHub certificate. Here, this is me, I have the certificate, here's my name, here's my public key. But then Alice needs to verify that the certificate is actually owned by Bob, because a certificate is a public thing. I can take my driver's license and give a copy of it to each one of you, a copy of it, not the actual one. And you can go ahead and show it to others, but I don't know it's actually yours, because we have the certificate. So for that, we use a bit of cryptography, and Alice gives a challenge to Bob. What she can do is she can take the public key, she can create a random string, encrypt it with the public key, and send it to Bob. Now, asymmetric cryptography tells us that if we encrypted something with a public key, only the entity who owns the private key can decrypt it. Okay, that's the basis of all the security we use today. And the private key should be kept private. Bob, if he has the private key, can issue with a response to the challenge and give her, okay, that's what you sent me. And now we have trust. Optionally, Alice can identify herself to Bob much in the same way, and then we have what is called mutual authentication. But this is a simplified version of how a TLS connection works with certificates. So once we have this knowledge, we know what a PKI is, we know what a certificate authority, we know what a certificate is. How do we build one with .NET in a serverless manner? That's what you're here for. When we come to build a certificate authority, the first thing we need to think about is the root certificate. What is the root certificate? Like I said, for example, we have GitHub. GitHub certificate is issued by a certificate authority, which is DigiCert in their case. And how do we know it's issued by DigiCert? It's signed by DigiCert's own certificate. So each certificate authority has their own certificate, which we sometimes refer to as the root certificate. And if I, for example, go back to the GitHub example, let me open it again. I can go here to certification path, and you can see that the leaf certificate is actually signed by this certificate, which is signed by this certificate. This is the root one. Okay, so here we can build also a chain of trust. In our case, we didn't want to build a chain. We had like a simple two-level thing. Now, the root certificate is the most important thing you need to keep private. If you leak your root certificate, the private key of the root certificate, basically whoever got it can provide certificates under your name and your entire security system is lost. Okay, so better keep it tightly under control. Now, we didn't want to invent the wheel here. We didn't want to work hard to securely store and manage the certificate and use it, because it's not only storing it, it's also using it to generate other certificates. So we decided to use a service in Azure, which is called Azure Key Vault. Now, Azure Key Vault is a service whose whole purpose is to keep cryptographic keys, certificates, secrets, connection strings, and any other sensitive information that you want. It can store it securely and allow you to manage who can access it and perform all kinds of cryptographic operations without ever getting the private key out. It also offers something that is called a hardware security module as a service, where you can actually store the secrets and use them to encrypt and decrypt or sign things without it ever leaving the specialized hardware that they're running for you in the cloud. Now, if you're not using Azure, you can definitely replace it with AWS Certificate Manager if you want to do it on AWS. Obviously, the implementation details that I'll show will be different, but the idea will remain exactly the same. The principles will remain the same. So in my entire session, Azure Key Vault is the only part which is Azure-specific. You can replace it if you want. All the rest, the serverless, the Azure Functions, you can definitely host it on other platforms as long as you see the code and you understand how it works. As I said, our scenario is that once a device leaves the factory, we have an employee who has an identity. That employee runs a certain script or utility on the device, and this process can also be automated. It doesn't have to be a human intervention. The employee authenticates itself, meaning we want to make sure that this person, this entity, has permissions to issue a certificate for the device. The device in turn turns into Azure function to a backend to issue this certificate using the credentials. And then the Azure function goes to Azure Key Vault to actually go ahead and issue the certificate that we wanted. So this is the flow we want to create. This is what I'm going to show you. Now, in order to set this up, we need to create some resources in Azure. So if you later on look at the code, and you'll see you have multiple branches here for all of the steps. So the first branch is setup. You have here a piece of code which creates everything you need. So we have a method for create a vault, an IoT hub, device provisioning service, everything. Let's look, for example, at creating a key vault. I'm using the Azure Management APIs to create it. So you see I'm creating a Key Vault Manager. I authenticate myself, give it a name, the region, all of the settings, and then I can go ahead and run it. You can also obviously do it in PowerShell or directly through the portal. Just created it, so if you want to play with it later, you can just run it and it will create all the required resources for you. So this is running. It's creating all the resources we need. We'll get back to that in a second. So we have our resources. The first thing that we want to do is generate the root certificate on Key Vault. Now, it looks something like this. We have a client, which is the Key Vault client from the Key Vault SDK. It has a method create certificate async. Now, this method generates a certificate on the Key Vault. Okay, it generates on the Key Vault and returns a reference to you. We give it the vault URL, our Key Vault identifier. We give it the name we want for the certificate. And then we have this policy object, which specifies all kinds of policies that we want in regards to our created certificate. So we give it things like, we want to have an RSA key, and RSA is the encryption algorithm. We can use other algorithms as well. We want this key length. 2048 is rather standard for an RSA key. You can have stronger keys with 3,000, 4,000 bits, but then your cryptographic operations will be harder. You'll need better hardware to perform them. We give it the subject name. This is the identifier of the device, of the certificate authority. We tell it that the certificate is going to be used to sign other certificates. Okay, all of these are what I said before, X509 extensions. These are metadata on the certificate. And EKU is an enhanced key usage, again, another extension of certificates, where we say these are what is called an OID, object identifier. These two numbers, what they say is they want this certificate to be used for server authentication and client authentication. These are the most basic extended key usages that you can find. There's rather standard. And then I say one last thing. I want the certificate to be signed by itself because it's a root certificate. At this stage, I could specify another issuer if I have another, let's say, DigiCert or any other certificate authority sign my root certificate. I could do that, and I actually encourage you to do so in production. In our production system, our root certificate was signed by another certificate authority, trusted certificate authority. For this demo, I built it with a self-signed certificate, which is good enough, but again, in production, you might want to change this part a little bit. Now, the good thing about this method is that if I would have used it, then the certificate is created on Key Vault, and the private key never leaves Key Vault. The object it returns only contains the public parts. We never get the private parts. The private key, which is the most important thing, is always remains on Key Vault. However, unfortunately, there is a small problem here because Azure Key Vault currently doesn't support creating a certificate which is used for signing other certificates. This method, create certificate async, is only good if you want to create certificates which are leaf certificates, let's say for the devices. So this is quite unfortunate, and it will actually let you run this code, but you'll only fail later on when you try to use it to verify another certificate, and you'll say, well, this is not good. And I don't know if they're going to change it anytime soon, but I still wanted to show you the code so you get the idea. Instead, as a workaround, what we did in our solution, is generated the root certificate on our machine and uploaded it. Now, the problem is that the private key is created on our machine, and then we upload it, and then we remove it right away. But it was still there for a short amount of time. And if you feel your device is secure enough, then that's great. If not, then it's a small problem. But again, for our scenario, when we run it on secure devices in a secure network, it was good enough. So what we did for this scenario is that, and this is all pure.NET, we have a classic .NET called RSA under system.cryptography. We create a key, and you see I'm using the using keyword because we want to get rid of it as fast as we can. We don't want the private key in memory any more than we have to. Sorry. We create the subject name. This is the name of the certificate authority. We create something that's called a certificate signing request, which is the way we create certificates. in .NET and in the world. We give it the certificate name, the key we just created, along with the algorithms we want to use. We add the extensions that we want. Again, we specify that the certificate is used for signing other certificates. And you see this tiny tidbit here, X509 basic constraint extension. This first true right here, if you later on go to the code and look, it says that this is a root certificate. It's allowed to sign other certificate. This is exactly what Key Vault doesn't allow us to specify. And that creates a problem later on. I give all the extensions, and then you can see certificate, create self-signed. We have the certificate, and then we use the same Key Vault client, only instead of create certificate, we use import certificate, which uploads it. So let's see it in action. We go back to our code. Here we go, it was all created. We can go to the portal. We can close this. We go to the resource group, up, back to the resource groups. Here, build PKI sample. Let's remove this. And we can see we have our function app, our IoT hub, our Key Vault, and so on. So now we want to create our certificate. So let's go to Visual Studio, take out our next branch, root certificate. We have another class here, which got added in this branch, where let's compile it. Where you can see we have a method, generate root certificate, and we have both methods, created in Key Vault or created self-signed and upload, where over here we created and then we import it. So let's run this. Let's hope it will run also. Okay. So it goes ahead, it runs the code I just saw you, creates the certificate and uploads it. And here we go. It created the certificate and uploaded it to Key Vault. I also stored the public part of the certificate on the machine because I'm going to need it later. This is only the public part. It only has the public key. Let me show it to you. Here we go. Root cert. You can see it's not trusted. It's self-signed. Build PKI sample CA, issue it. And we have all the details, much like before. But we also have it on Key Vault. So if we go to the portal, go to Key Vault, and go look at certificates, we can see we have the root certificate here. It's expiration a year from now, so we created it right now. I have here all the versions from previous runs of this while I was building the demo, but here's the current version. And we can see it was created just a minute ago. Okay, so we have it here with all the details and the subject name and issuer and everything. So we have a certificate in Key Vault, a root certificate. But how do we use it to generate the other certificates that we have? First of all, once we generate the certificate, we want to secure it because we don't want no one to access it. Remember, this is the most important thing. So you have something in Key Vault which is called Key Vault Access Policies, which allows you to limit who can access this certificate. So in our case, what I did is I allowed the API, the Azure function, access to only get the certificate, and this is the public part of the certificate, not the private part, and allowed it to sign things using the certificate. Now you can see here that it doesn't have the permission to get the private key. The private key never leaves Key Vault. Again, this is the most important thing. You don't want the private key to ever leave Key Vault. No one should have the authority to do that. Now, not only do you set the access policy, you can also set some auditing rules. So in the end, in the slide deck, you have a link of how to set the auditing rules. But basically what Key Vault can give you is it can give you a log of every access to your Key Vault, to your certificate, and what was done with it. So you can see an example here where for an audit entry, where you can see this is a get on the vault, and the result was OK, and this is the IP address. And most importantly, we can see who is the identity who created the operation, and some additional information regarding the URL, the ID, and so on. So you can get quite a lot of information by auditing Key Vault. So we have the root certificate, we have it secured, we have it in Key Vault. Now we want to use it to sign other certificates, the device certificates. Let's look at the flow more in depth. We have a device this device is going to generate a key pair. It's going to generate its own public key and private key for its own certificate on the device. Now, the private key will never leave the device, only the public key. Okay, so it is generated on the device. In addition, the device authenticates, I won't say itself, remember we have the employee running the script on the device or the automated process. We need to verify the automated process that it is allowed to generate certificates. So we're going to use an identity provider. In our case, it's going to be Azure Active Directory to identify, to authenticate the person issuing the certificate to the device. We get some sort of access token, and then we send to the certificate authority the subject name, the name of the device that we want, the public key which we just created over here, and the access token that we got when we authenticated. The certificate authority will verify the access token. It will generate the certificate signing request, and it will send the hash of the certificate or the digest of the certificate just created here with the CSR to Key Vault. Now, Key Vault will sign this digest using the private key. Again, the private key doesn't leave Key Vault. We send something up to be signed by the private key. It is returned signed. Then we put it back in the certificate, and we return a signed certificate back to the device. The device can now take it, combine it with the private key, which never left the device, and store it somewhere in a secure storage. Now, in a regular device, this would usually be some sort of hardware security model on the device, an HSM or a TPM, a trusted platform module. In our case, in this demo, we're just going to store it in the operating system certificate store, the basic store which you can use. And for the first part, we're going to focus on this area, on the server side. We're going to go back to the client side. So we get a request, we generate the CSR, go to Key Vault to sign, get the signed object, and return. So that's what we want to achieve at this phase. So how do we generate the certificate sign request? That's rather easy. Note. We create something that's called RSA parameters, then we call RSA.create. Remember earlier when we said RSA.create without any parameters? That created a random key. Here, we got the public key from the device. This is an input. Okay, the exponent and the modulus are parameters of the public key. That's what represents the public key in RSA. So now we create a certificate key, which is only made up of the public key that we got from the device. Once we have that, again, we give the certificate name over here. We create the request with the name and the certificate key we got. We add all the extensions we want. In this case, we don't want to sign other certificates. We want to be able to digitally sign things to prove we are who we say we are, and also encrypt things. This is what we need in order to support TLS authentication later on. And note this time, the false here says that this is not a root certificate. This is not supposed to sign other certificate. This is a node certificate, a leaf certificate. Then we return the request. So we have a certificate signing request. So far, this is all pure.NET, okay, system.cryptography. Now we need to sign it with the root key in Key Vault. So we have the request. In addition to the request, we need to create some sort of serial number, because every certificate authority, when it generates certificates, it needs to give every certificate a unique serial number, which cannot repeat itself. So in this case, I implemented with a simple blob storage, but you can do it with Redis, with table storage, with SQL Server, with whatever storage mechanism you want. The implementation is quite simple. You can also look at it later at the code. Once I have the request and the serial number, the next step, and this is the important part, is to get to the Key Vault client from the Key Vault SDK and note this method, toRSA, which returns an RSA key. Now, this extension method comes from a third-party NuGet package. It's an open source package. It was created by an Azure MVP called Oren Novotny. I don't know if you've heard of him. You have the link at the resources slide at the end. And what he did is he created an implementation of a .NET RSA key where every sign operation, encrypt operation, decrypt operation, instead of performing it locally, it goes to Azure Key Vault, performs it there, and returns the result. And basically what it did, because we returned a .NET RSA key, you can use it anywhere .NET expects to get an RSA key, and use Key Vault transparently. So that's really nice, because once we have that, we continue, we create something that's called a signature generator, again, part of system cryptography. And we get to the important part where we create the certificate, we give it the name, we give it the net generator we just created, which encapsulates the Key Vault client eventually. We give the validity period and the serial number, and this returns a certificate according to parameters we got, the subject name and the public key we got, signed by the root certificate, where the signature process was done on Key Vault without the private key ever leaving Key Vault, thus achieving what we wanted. Once we have the certificate, we can simply send it back to the device, and they can continue on with it. So let's see it in action. We can go to our demo, get our next step out. Let's close this. OK, we have a couple of more projects here. So if you look at it later on, you'll see that there is one project for the business logic of the certificate authority. And there's one project for the, and that one contains all the code I just showed you. You can see we have here the serial number generator and the issuer that I just showed you, where it goes ahead and creates all the objects I just showed you. And you have another method, assembly, which basically only contains the function. It exposes an Azure function with post. It gets the public key and the subject name from the request, from the device which sent us these, creates the certificate issuer, and then basically encodes the result in base 64 and sends it to the device. Now, if you don't want to host it in Azure Functions, you want to host it in something else, you can do it pretty easily. You just need the business logic. Now, I'm going to take this API I just created. I'm going to publish it to Azure. So we have it here. Let's click Publish. And until it publishes, what I want to show you is that as part of the resources setup, the script I ran earlier, I did something very nice. We'll go to the Azure function. Here it is, right here. And remember, we need to authenticate that the entity who is running the function actually has permission to do it. We don't want anyone just be creating certificates. So here we used a feature of App Service, Azure App Service. It's called App Service Authentication or Easy Authentication. Some of you may know it. And we can click here. And we can see that it's configured so any action, any request which is not authenticated will be logged in with Azure Active Directory. And we have some configuration of how to validate this with Azure Active Directory. I'm not going to go in-depth into this. Again, if you want, you'll have the code. You can see the script and see exactly how it is set up. But we have authentication built in. Again, if you don't host it in Azure Functions, you'll need to come up with your own authentication mechanism of how to verify who is allowed to create a certificate in the first place. All right, so we deployed our certificate. This is done. Deployed our Azure function. This ran all the way. And once it's deployed, we want to start using it. We want to start generating certificates with this root certificate. Now, I showed you this before, but in this phase, we'll focus on the client side. How do we generate the key pair? How do we request the access token and store the certificate securely on the device? So first, we need to get an access token. The first step is to authenticate with Azure Active Directory. You can look at the code later. Basically, you can use something like Azure Active Directory Authentication Library, ADAL, or MSAL, which is Microsoft Authentication Library, which is what I used in the demo. I'm not going to show you the code here. It's pretty straightforward and well documented. Once we have the access token, we need to authenticate ourselves with the certificate authority, with Azure Functions. So we take the access token that we got from Azure Active Directory. We serialize it into an HTTP request, and we post this request to this URL on the Azure function, .auth/login/AAD. And this is the way you authenticate with the app service authentication feature, the one I showed you a moment ago. Now, once we have that, we can read the response, and we get a property called authentication token, which is something we can send to Azure Functions, and then Azure Function can authenticate our identity. So we got an access token for Azure Functions. Now we want to issue the certificate. So what do we do here? First of all, we create an RSA key, again, a random key. We're using the default implementation. You can modify the key length and how it is generated and so on. We export, not false here states that we only want the public parameters. We don't want to export the private key, just the public key. And then we create a request. We give the name of the device that we want to generate the certificate for and the public key. Once we have the request, we put it in HTTP string content. We create the client with the base address of the Azure function. We add the access token that we got. We need to add this header. This is what the header is called for app service authentication. We post it to the Azure function, and we get back our response. Remember, the response contains a base 64 encoded certificate. So we read the response, we get the deserialized object, do from base 64 string, get the certificate. We create an X509 certificate around it, and we have our certificate on the device. So we create an access token, we sent a request to the Azure function with the public key, got back a base 64 encoded certificate, decoded it out of base 64 into an X509 certificate, and then we have it. Now we need to store it somewhere. So if we want to store it, what we can do is we can use the default operating system store. So in this case, you can go and say certificate, which is the public certificate we got. We add the private key because remember the private key never left the device. So we want to combine the private key with the certificate we want. We want to store them together. And then we run into a problem if we run this on Windows, because if we were to continue and store this thing on using .NET Core on Mac and Linux, this would have worked great. On Windows, this actually doesn't work, because when we created the key, if I go back a bit, we used the default RSA implementation, which sadly doesn't allow storing the private key later on. So we have two ways of solving it. Either use the overload, which takes another provider, and then you can store it later on, or, and this is actually recommended by Microsoft in one of the GitHub issues, you could work around it. You could export the certificate into a pfix file in memory, and then re-import it, only this time specifying that the key can be persisted. So this is a hack. It's a workaround, but that's the best way to do it on Windows, and it will also work on Linux and Mac, so you don't need to create the various flows. And then you open an X509 store, you open it, add it, and it's stored. Let's see it live. So I'm going to go here, check out the next step of the way. Okay, it's going to check it out. Let's set it as the startup project. Let's run it. Okay, so now it's going to want us to authenticate ourselves because we're the employee who's creating the certificate. We got the code here. This is called the device code flow, where we get a code, we paste it in here, we choose our identity, and we're signed in. The device should recognize it in a second. Now, I'm running it on Windows, but it's .NET Core, so you can run it on any platform, on Linux as well. Here we go, we're authenticated. We want a certificate named My Device. Okay, that's good. Let's confirm. This is sending a request to the Azure function, and look, we got our certificate back. We have the subject name My Device. We have the issuer build PKI sample CA. We have a serial number, validity dates, thumbprint, everything. And we actually have it stored in the certificate store, because if I go to the manage user certificates and I go to personal and go to certificates, here we go. my device, signed right here. Okay, so we have the certificate on the device. We got it issued from the certificate authority. But let's complete the cycle. Let's complete the flow end-to-end, because remember, in the beginning, we want to have something like this, where we go to device provisioning service, get back the IoT hub we need to talk to, and send the data. How do we use the generated certificate to identify ourselves? So that's rather easy. We simply load it up from the certificate store. Remember, we stored it earlier. You just open the certificate store, load it, and that's it. Using the Azure IoT SDK, we have something called security provider certificate, X509 certificate. We give it the certificate, and then we run some code which eventually registers us and sends the data. Again, this is the less important part for a session, but I just want to show you end-to-end how it works. So let's go back to the portal. Let's go to the resource group. Up, too far. OK. Now I want to go to our device provisioning service, and I want to configure it with the root certificate that we had for our CA, so it will recognize our certificates. So we'll go to certificates. OK, we're going to add the root certificate which we created earlier. Note just the public part. We don't never give it the private part. So let's call it CA. And we need to upload the certificate. Now, if you remember, I told you that I stored the public part of the root certificate earlier on the file system. That's why. So let's copy the path, paste it here. So I'm uploading the public part of our root certificate. And we have it here. And note, it's unverified. Why is it unverified? Because it's public. Anyone can have it. Anyone can steal it. IoT Hub needs, device provisioning service needs to know that we actually own the certificate. How is it done? With a challenge, remember? It needs to challenge us, and we need to respond. So we can click here. We can go here, generate verification code. It generated a challenge. What we need to do is create a certificate signed by the root certificate whose subject is this. How do we generate a certificate? Let's run our tool again. So let's run our utility from before. Let's authenticate ourselves once more. Paste it here. Click Next. OK. Authenticate. Here we go. But now, instead of my device, let's get the code from here. No. Paste it here. And now we'll get a certificate whose subject is this. And conveniently enough, I also store the public part on a file. So we can go here, select this file, upload it, open, verify. And here we go. We're verified. And when this is running, we can go to enrollments, which is how we specify the devices that we want to enroll in the device provisioning service. We add a group because it's signed by the CA. We give it a name, my devices, certificate, CA certificate. Here we go. This is the certificate we just created, CA. We need to link it with an IoT hub. So let's link an IoT hub to it. Let's choose the one. This is the one which was created by the script. Give it the access policy, save. OK. Hopefully it will be fast enough. And this is the part where I have to pray to the demo gods because we're almost at the end. Here we go. Let's select the IoT hub we just created. Let's save. So we created an enrollment. What we basically told device provisioning service is every device with a verified certificate signed by our root certificate, allow it through. Assign it to the IoT hub, give it a credential, and let it continue on. And once we did that, we can go back to Visual Studio, get back our last part, which is the actual device code. Let me set up as a starter project. I'm not going to go in depth into the code, but you can see I'm loading the certificate, registering the device, and eventually sending an event. Okay, so let's set a breakpoint here. Let's F5 into this. So the device loads up, wakes up, loads the certificate from the certificate store, goes to device provisioning service, gets registered into an IoT hub, and eventually it can send an event, and we're done. We completed the flow end to end. So it amazes me every time it works for the first time, because you know how cloud works. You never know how it ends. So just a few things I want you to remember from this session. Certificates are hard, okay, but they're crucial to get right. You don't want to mess up security. You don't want to mess up certificates. You don't want to author an entire PKI by yourself. You have plenty of off-the-shelf solutions, but if you have your own unique requirements like we had, you can definitely tailor-made it to your requirements. In our case, .NET Serverless. Now, I use it for IoT. You can definitely use it for other scenarios as well, where you need to manage multiple things with certificates. And handling certificates in .NET is surprisingly undocumented. Okay, so you better do it right. You have to look a lot. Again, you have this demo you can look later on to base yourself on. And Azure Key Vault is a great basis to create a certificate authority. So here you have all the resources that you need. You have the GitHub repo, you have the NuGet package, you have the additional resources. If you want to take a quick snap of it. And that's it. Thank you very much for your time. We're now going to have time for questions. Thank you. Yeah.
Thank you. This question is two parts. First part, do you use this solution to production for all customers?
Yes.
Okay, second question. You have positive result. We develop other part or other pieces of this umbrella about, for example, certificate revocation and other part?
That's a great question. So the production solution, that's not the entire production solution. The production is actually a bit more complex because we give a certificate to each factory, and then we can revocate specific factories if their lifetime is revoked. But what we do eventually, the way we revoke the certificate is that we don't actually revoke it. We simply remove it from the device provisioning service, so it no longer recognizes the certificate. And the next time a device comes in with that certificate, it will have no way to authenticate, and then to require a new certificate. That certificate basically becomes worthless.
If I understand correctly, you use like some pieces of the typical PKI management tasks. Yeah, not for example, key management, certificate management, typical. Tasks
so we don't do classical certificate management per se in our solution, because since the certificates are only used for the device provisioning service, we manage it from there because we can revoke. What we did is that we renewed the root certificates or the intermediate certificates on a daily basis. That way we could fine-grainedly revoke certain parts of the devices manufactured. If we, for example, find out that something was compromised.
Reason is my question. It's nice idea, make like serverless PKI CA functionality, but for me, I do not understand now, do you have positive results for cover all PKI functionality or only part by these technologies?
So since what we did is the existing part we used was Key Vault, which allows us to manage the certificates, in our case the root certificate, and also the intermediate certificates. So it doesn't have a mechanism to revoke them or to manage them. Actually, there are some parts, because, for example, if you want to monitor that the certificate is still valid, you can register actions in Key Vault where you can say, I want to be notified by email or by some other medium where a certificate is about to expire. So we can use that, for example, but the revocation we didn't use Key Vault, we did it ourselves.
Okay. Thank you. I have a question regarding the initial certificate generation. Basically, the weakest point here is, from my experience also, is how to authenticate a device in order to allow it to generate a certificate. So as I understood, it's a device where like a person logs in, and what if it's a headless device which doesn't have any GUI
so that's
whatsoever?
A great question. So in what I showed and what we did actually also, because the device manufacturing rate is pretty low. Again, it's going to be a few thousand in a few years. So a human being actually went to the device and ran a utility on it. It's Linux-based, so it ran a utility on it and just got it to work. Now, what you could further glue, for example, if it's a headless device or the manufacturing rate is high, so what you can do is you can have the device expose, let's say, some sort of endpoint or endpoint, and have another service running inside your factory, which has its own identity, and that identity is allowed to issue the certificates. And then what you can do is can actually go and issue the certificates directly and send them to the device, or if you don't want the private key to leave the device, you can actually get an access token for a short period of time, even for 5 minutes or 1 minute, give it to the device, and the device can go and get the certificates for itself. So you can basically do that.
Yeah, I'm afraid time of the lecture has come to the end. Let's thank our lecturer with an applause.
Thank you, and I'm still around.